position vector, displacement vector, velocity vector. We call it as the position vector. Initial position vector is represented by So in the last video we discussed about unit vectors. Now in this video we will discuss position vector and displacement vector, and finally the velocity vector. So let's start with the first topic. So position vector. Now if you remember that in second chapter we discussed a position vector, displacement vector, velocity and accelerations vector in one dimension. Now we'll discuss all these vectors again but in two dimension. So consider this two-dimensional coordinate system. So this is our positive x-axis, positive y-axis, and this is the origin. Now suppose a person is standing here. So its position vector from the origin is represented by this vector. And this vector is r vector. So this vector we call it as the position vector. And we have discussed the unit vectors. We can split this the position vector into two components, into two vector components. The first one is along the x-axis, positive x-axis, and this is along the positive y-axis. So the vector component along the positive x-axis is rx, x cap, and along the positive y-axis is ry, y cap. And we can also write here that the position vector r is equals to rx x cap plus ry y cap. So this is all about position vector. Now next we'll discuss the displacement vector. Now we'll discuss displacement vector. So consider this two-dimensional coordinate system. So this is positive x direction and this is positive y direction. Now suppose your initial position is here and you start walking in some direction, any direction you can take, and you stop somewhat here. So this would be your final position. So this I can write, this is I, initial position, this is F, the final position. So your position vector, initial position vector, is represented by this arrow. This we can write Ri, and I is for initial. So this is a position vector. Now the final position vector is this one. This I can write Rf. F is for final. Now the displacement. So displacement vector is obtained by joining the head of initial position vector to the head of final position vector. So this is what we call the displacement vector, and this is the displacement that you traveled. This is delta r, and this is a vector. So for vector we just write an arrow above it. So from the definition of displacement vector we can write that the displacement vector is equals to Rf, the final position vector, minus Ri, the initial position vector. We can rearrange these terms and we can write that Rf is equals to Ri plus delta r. This means that the final position is equals to the initial position of the body plus the change in position. So this is all about displacement vector. Now next, one more thing, the SI unit we have in meter. Now next we're going to discuss the velocity vector. Now in second chapter we studied that velocity is defined as displacement over elapsed time. So the average velocity vector, which we write this way, this is AV, the average velocity vector, is equals to the displacement vector, that is delta r, this is just we studied right now, divided by the elapsed time, which is delta t. So this is the way we define the velocity vector. and the SI unit for this is meter per second. And here we see that this delta r is a vector and delta t is a scalar. In other words, we can say that velocity vector is obtained by multiplying displacement vector with a scalar number, which is 1 over delta t. And one more thing, here delta t is scalar and this term is a vector. So the direction of average velocity vector will be same as that of the displacement vector delta r. Now let's take an example based on average velocity. So suppose that this is the initial position of the dog and he started walking in this direction, then it stopped here. So this would be the final position of the dog. Now this Ri represents the initial position vector, which we are given in the question to be Ri vector is 4.60 meter x cap. This is the x component of vector plus 0.960 meter y cap, and this is the y component of vector. And Rf, the final position vector, we are given to be 0.520 meter x cap plus 2.40 meter y cap, and we need to find the average velocity of the dog. Now we studied just now that average velocity vector is equals to delta r over delta t. Now delta r is the change in position, or you could say the displacement vector. So delta r, this would be equals to Rf minus Ri. We have to subtract the final position vector minus the initial position vector. So let's put the values. Rf, we have this thing. So this is 0.520 meter x cap plus this is 2.40 meter y cap minus Ri. Ri we have 4.60 x cap plus this is 0.960 meter y cap. Now let's subtract the x component with the x component and y component with the y component. So this we can write 0.520. This is the x component for Rf minus the x component for Ri is this value 4.60. This is x cap plus this is 2.40 minus 0.960 and this is y cap. So this would be equals to minus 4.08 meter and then x cap plus 1.44 meter and this is y cap. So this is the displacement vector delta r, which is represented by this arrow, this delta r. Now we can easily calculate delta. Now one thing I have missed it out, that delta t, it is given in the question to be 3 seconds. The dog took 3 seconds to move from the initial position to the final position. So we can simply put delta r here and delta t here to find the average velocity. So this is average velocity vector. Delta r we have negative 4.08 meter x cap plus 1.44 meter y cap divide by time we have 3 seconds. So this is 3 seconds. Now we can further solve it and we'll get the final answer to be minus 1.36 meter per second. The unit will convert into meter per second, and this is x cap plus 0.480 meter per second and this is y cap. Now here this would represent the x component and this would be the y component of velocity vector. Now one thing I'm going to ask to you guys, that what would be the direction of the velocity vector? Pause the video and think. Now I hope you tried. Now the direction of velocity vector will be same as that of position, this displacement vector. So you can write that the direction will be just parallel to this position vector. This would be the direction for the average velocity vector. So one final concept is left, and then we're going to end this video. So consider this graph, and suppose a body is moving along this curve, and at time t1 the position of the body is at this point, let it be p1. Similarly at time t2 the position of body is at this point, let it be p2. Now this arrow will represent the displacement vector for the body during this time interval. And just now we studied that the average velocity vector points in the same direction as that of displacement vector. So this was about the average velocity. Now what about the instantaneous velocity, the velocity at a given time? So for that, if we have to consider the smaller time interval, and mathematically we write that the instantaneous velocity vector is equals to limit delta t approaches to 0 delta r over delta t. This is the way we represent the velocity vector mathematically. Now what about how we can represent the velocity vector on this graph? So the instantaneous velocity vector at a given time is tangential to the path of the particle at that time. So simply we have to make a tangential arrow at that point, and this vector will tell you the direction for the instantaneous velocity. Similarly at point 2 this arrow will tell you the direction of velocity vector, and the length of the velocity vector will tell you the magnitude of the instantaneous speed of the body. So we can find two things from velocity vector. The first one, the instantaneous speed, and second one, the direction. So you need to note one thing, that the instantaneous velocity vector points in the direction of motion at given time. So at this position the direction of motion is along the velocity vector. Similarly at this position the motion is along the velocity vector. So this is all about the instantaneous velocity. Now based on the concept that we have just studied, I'm taking one problem. So suppose that the velocity vector for a particle is given us, which is v vector is equals to 2.6 meter per second x cap plus minus 1.9 meter per second y cap, and we need to find the speed of the particle. So speed of the particle will be magnitude of the velocity vector, and the magnitude of the velocity vector is given by under root, now x component square, which is 2.6 and it's squared, plus the y component squared, which is minus 1.9 and it's squared. So this comes out to be as 3.2 meter per second. So this would be the speed of the particle at the given time. Now suppose we need to find the direction also. What would be the direction? Is theta. So theta would be tangent inverse the y component, which is negative 1.9 divided by the x component, which is 2.6. So this comes out to be as minus 36 degree. So what this minus sign denotes, that the direction of the particle is 36 degrees below the x-axis. Let me show it in the figure also. If this is positive x-axis, this is negative, and this is positive y-axis, then the direction of the velocity vector something like that, and this is 36 degree, and the magnitude of this velocity vector is this thing, which we call it speed, the instantaneous speed. So this is all in this video. Now in the next video we'll discuss the acceleration vector.